Section. Introduction. The introduction of large language models, LLMs, has significantly transformed the field of natural language processing, demonstrating impressive skills in a range of real-world tasks. However, LLMs still have limitations in certain areas such as programming, mathematics, biomedical, or finance. This hinders the development of universal language agents for wider applications. Previous research has tried to enhance the diverse abilities of pre-trained LLMs using specific data strategies. While this is possible, it demands considerable computational resources and large data volumes, which is a hurdle to making LLM research more accessible. As a result, another research direction, known as domain adaptive pretraining, concentrates on post-pretraining with domain-specific data. These methods have proven effective in adapting various LLMs to specific domains, leading to improved performance on downstream domain-specific tasks with less computational expense. However, a significant challenge arises in the form of catastrophic forgetting. Post-pretraining often results in a decrease in the model's original general abilities, which hampers the fine-tuned performance of the model on a variety of tasks. This calls for a method that can infuse domain-specific knowledge into LLMs while maintaining their general abilities, thereby boosting their overall capabilities. To address this, we present a straightforward yet efficient post-pretraining method, called block expansion. We enlarge the pre-trained LLM using duplicated transformer blocks. The newly added blocks, whose linear layers are initialized to 0 to allow identity mapping, are further fine-tuned with only domain-specific data while the remaining blocks are kept unchanged. After fine-tuning, the expanded pre-trained model excels in both general and domain-specific tasks. In practice, we extend the pre-trained LLAMA 2.3B by adding 8 more blocks, resulting in LLAMA Pro, a foundational model with 8.3 billion parameters, and improved performance in programming, coding, and reasoning. We pre-train LLAMA Pro's expanded blocks on 80 billion tokens using open-source code and math data for 2,830 GPU hours, 16 NVIDIA H800 GPS for about 7 days. We further perform supervised instruction tuning, full fine-tuning of all the blocks, also known as SFT, on LLAMA Pro with approximately 80 million tokens, resulting in LLAMA Pro Instruct. It's worth noting that pre-trained models produced by our block expansion method are fully compatible with the subsequent SFT techniques without any specific modification. As demonstrated in the figure, LLAMA Pro Instruct achieves top performance across a wide range of general, code, i.e., human eval, and math, i.e., GSM-8K, tasks. Moreover, we evaluate the capabilities of LLAMA Pro Instruct as a language agent across various scenarios, i.e., Mint Bench, focusing on the tool usage abilities and the capacity to ground in environmental and human feedback. We also use GPT-4 automatic evaluation to assess LLAMA Pro's ability to serve as an effective assistant, i.e., MT Bench. Comprehensive experimental results show that LLAMA Pro Instruct outperforms other models from the LLAMA family on both benchmarks and practical applications. Our contributions are threefold. 1. We propose a new post-pretraining method for LLMs, called block expansion, which allows the injection of new knowledge while preserving the initial capabilities. 2. We introduce LLAMA Pro and LLAMA Pro Instruct, versatile LLMs that effectively integrate natural and programming languages, excelling in general tasks, programming, and mathematics. 3. We benchmark the family of LLAMA Pro on extensive datasets, including both traditional and agent-oriented tasks, demonstrating its superiority and great potential in broader complex applications. Related work. Advancements in large language models. The field of large language models has seen significant progress in recent years. The increase in model and data scale has been crucial in achieving top performance across various tasks. At the same time, the development of more generalist models has led to the creation of models that can tackle diverse problems and quickly adapt to new tasks. These advancements have been further supported by the open-source community, which has released powerful open large language models for research, such as LLAMA and Code LLAMA. Our work builds on these developments by providing a methodology for specializing large language models in the domain of code, paving the way for future research and applications in this area. Post-pretraining. Language model applications typically involve a two-step process, an initial general domain pretraining step, followed by domain-specific training. The fine-tuning step is often aimed at enhancing instruction following abilities or aligning the model's outputs with human preferences. Additionally, some studies explore adapting pre-trained models to new domains using parameter-efficient fine-tuning methods. Many works also focus on how to do continual learning after the pre-training phase. In our work, we propose an adaptation strategy that combines continued training with targeted general capability maintenance, allowing large language models to specialize in specific tasks without sacrificing their overall performance. Section Summary. The introduction discusses the limitations of large language models, LLMs, in certain domains and the challenges in improving their capabilities without requiring excessive computational resources and data. The paper proposes a post-pre-training method called block expansion, which adds new transformer blocks to the pre-trained LLM while preserving its general abilities. The extended model, LLAMA Pro, demonstrates enhanced performance in both general and domain-specific tasks, making it a versatile LLM for programming, coding, and reasoning. Section. Progressive learning. In recent times, the concept of progressive learning has been gaining traction due to its potential to speed up the training of large-scale models in fields like computer vision and natural language processing. Some researchers have suggested a method that doubles the model's depth at each stage, while others have proposed a method that allows for the expansion of the hidden size of features. Our approach uses depth growth to maintain overall performance while adapting to a specific domain. Let's talk about the LLAMA block. This block is made up of a multi-head self-attention mechanism, followed by a position-wise feed-forward network with residual connections and a swish-gated linear unit operation. If we have an input, x, the LLAMA block produces an output, y. The input, x, has two dimensions, the sequence length and the hidden size. The output, y, has the same dimensions as the input, x. The multi-head self-attention operation is a key part of the transformer. It involves query, key, and value matrices, and an output weight matrix without bias. Each head is calculated using corresponding weight matrices for that head. The feed-forward network in the LLAMA model uses the swish-gated linear unit activation function. Now, let's discuss block expansion. If we have a model with blocks, the block expansion adds an identity block after each block in the original model. This ensures that the expanded model maintains the same output after expansion. The identity block is such that the input and output are identical. If we have an initial model with L blocks that needs to be expanded to L' blocks, we first divide the original L blocks into N groups, with each group containing L over N blocks. For each group, we create identity copies of the top P blocks and stack them on top of each group. We arrange these blocks in an interleaved manner to maintain the structural characteristic of the transformer model. This process increases the depth of the model while maintaining its output behavior. However, there's a challenge when applying this approach to the LLAMA block. The gradient of the loss function with respect to the RMS norm weight during backpropagation would be 0. This would prevent the training of RMS norm. To overcome this, we initialize the weight matrices in the identity blocks to 0. As a result, the entire block is reduced to an identity block at initialization, preserving the output from the initial model. Our method focuses on the post-pre-training stage, targeting specific domain corpora such as code corpora. We start by initializing our model with large language models trained on extensive and labeled general corpora, where all blocks will be fine-tuned. To enhance the model's capacity for accommodating additional domain knowledge while retaining its general knowledge, we employ block expansion to increase the number of blocks in the large language model. During this process, we only fine-tune the newly added blocks while freezing the original blocks, thereby preserving the general abilities of the model. Section Summary. Progressive learning has gained attention for accelerating the training of large-scale models in computer vision and NLP research. This paper proposes a method called compound grow that extends stacking by incorporating feed-forward network, FFN, expansion into the schedule design, allowing for the expansion of hidden size of features. The method employs depth growth to preserve general performance while adapting to a specific domain, such as code corpora. Section. Experiments. In this section, we'll share the main findings from our experiments. We'll start by outlining the experimental setup, then we'll discuss how we tested the effectiveness of block expanded tuning after pre-training. We'll also share the results from our supervised fine-tuning, SFT, process, and finally, we'll present a study that examines the key design choices we made. To begin, let's talk about how we prepared for the pre-training phase. We created a dataset that focuses on code and mathematical content. For the code part, we used the stack dedup dataset, which is a collection of open source codes from GitHub, specifically the Python section. For the math part, we used the ProofPile2 dataset, which is a massive collection of scientific papers, web data with mathematical content, and mathematical code. We started with a base model called LLAMA 2-7B and increased the number of blocks from 32 to 40 using an interleaved method. During this block expansion process, we set the parameters to 1 for P, 4 for M, and 8 for N, which resulted in 8 groups where each group expanded from 4 blocks to 5 blocks. For the pre-training of the code and math corpus, we used a batch size of 1024, a sequence length of 4096, a warm-up ratio of 6%, a learning rate of 0.0002, and a cosine learning rate scheduler. We also used BF16 mixed precision, a weight decay of 0.1, and gradient clipping at 1.0. To speed up the training process, we used the flash attention mechanism. We conducted our experiment on 16 NVIDIA H800 GPS and trained LLAMA Pro for a total of 15,900 steps, which took about 2,830 GPU hours. During the instruction fine-tuning phase, we combined 5 data sources to create LLAMA Pro. Instruct. These sources include Shared GPT, which contains real user and chat GPT chat history records, and the Wizard LM Evolution Instruction Dataset, which provides a wealth of instruction data with varying complexity levels. We also used the Evolution Code Alpaca dataset, which includes complex coding tasks generated by ChatGPT and their corresponding solutions. Additionally, we used MetaMath, which reframes questions from multiple perspectives, and a curated subset of our OpenOrca data. This subset provides an efficient route to achieve performance comparable to using larger data slices, while only incorporating approximately 500,000 GPT-4 completions. The final SFT dataset consists of approximately 1 million samples. To fine-tune the basic models, we used specific configurations, including a batch size of 128, a sequence length of 4096, a warm-up ratio of 0.03, a learning rate of 0.00002, a cosine learning rate scheduler, and BF16 mixed precision. For the evaluation phase, we compared LLAMA Pro with the latest top-performing large language models, LLMs. We used the Eleuther AI Language Model Evaluation Harness, a unified framework designed to test generative language models across a wide range of evaluation tasks. For code-related tasks, we used the Big Code Evaluation Harness to evaluate human eval and MBPP, and we reported the pass at 1 rate of code tasks with greedy decoding. The benchmarks we used for evaluation include the AI2 Reasoning Challenge, HelloSwag, MMLU, Truthful QA, Winagrande, and GSM-8K. These tests measure a model's ability to answer grade school science questions, make common-sense inferences, multitask, reproduce falsehoods commonly found online, reason at scale, and solve multi-step mathematical reasoning problems. We also evaluated the models in the context of the program of thought (POT) setting, which uses Python code to solve mathematical problems. This serves to evaluate the code generation capabilities of the models. We used human eval and MBPP for this, which are sets of Python programming problems designed to be solvable by entry-level programmers. Each problem consists of a task description in English, a code solution, and 3 automated test cases. Section Summary. In the experiments, we first described the settings and datasets used for pre-training the base model. We then explain the process of block expansion and the specific parameters used. For supervised fine-tuning, we combine multiple data sources to create LLAMA Pro. Instruct. Finally, we outline the evaluation process, which includes benchmark tests for code-related tasks and general language understanding tasks, as well as assessments in the context of the program of thought (POT) setting. Section. Pre-train results. We've tested the performance of our model, LLAMA Pro, using various benchmark datasets from the Open LLM leaderboard. We've also included coding benchmark datasets like Human Eval Pass at 1 and MBPP Pass at 1, and the Math benchmark GSM-8K, to give a well-rounded evaluation. We compared LLAMA Pro's performance with other top-notch pre-trained models that were trained around the same time and of similar size. This includes general-purpose models like LLAMA 2 and code-focused models like Code LLAMA. Our results show that LLAMA Pro strikes a good balance between natural language processing and coding capabilities. It not only maintains the general performance of its base model, LLAMA 2-7B, but also surpasses it in the average performance of general language tasks. On the other hand, LLAMA 7B trades off general performance to enhance its coding ability. We believe this improvement is due to our expansion design, which keeps the initial LLAMA blocks to maintain their capabilities and adds more blocks to accommodate more domain-specific knowledge. LLAMA Pro shows strong general performance along with coding performance that matches code-focused LLMs. After fine-tuning with an additional 80 billion tokens in conjunction with LLAMA 2, LLAMA Pro more than doubles the average performance on coding tasks. In contrast, Code LLAMA is fine-tuned with 500 billion tokens. LLAMA Pro excels in general performance while keeping up with code-focused LLMs, whether they are trained from scratch, like StarCoder-15B and Crystal Coder, or fine-tuned like Code LLAMA 7B. Modern LLMs typically undergo supervised fine-tuning or instruction tuning after pre-training on vast amounts of unlabeled data. We've shown that our expansion strategy can adapt to this widely used training pipeline, just like traditional LLMs. As a single SFT model, LLAMA Pro Instruct achieves top performance, even when compared to specifically tuned models like Wizard Coder and Wizard Math. This shows its more comprehensive capabilities. We've also evaluated the comprehensive conversational performance of the LLAMA Pro Instruct Assistant using the MT Bench with GPT-4 automatic scoring, as proposed by Vicuña. LLAMA Pro Instruct outperforms widely used chatbots from the LLAMA community, indicating its potential as a chatbot capable of providing helpful responses, in addition to its impressive performance in traditional benchmarks. We've used Mint Bench to evaluate our model's ability to solve multi-turn interactions by using tools. Mint Bench tests LLM's ability to use tools by generating and executing Python code, focusing on tool-augmented task solving and leveraging natural language feedback. LLAMA Pro Instruct achieves top performance compared to similar size models in multi-turn interactions with the use of tools. We've evaluated various training strategies, including LoRa, fine-tuning, and the block expansion training approach that we propose, using the TRACE benchmark. TRACE is designed to assess continual learning in LLMs and comprises 8 distinct datasets that span challenging tasks such as domain-specific tasks, multilingual capabilities, code generation, and mathematical reasoning. We assess the ability of different strategies to retain the model's existing knowledge while incorporating new skills. We've found that block expansion training shows superior task-specific adaptability compared to sequential fine-tuning and LoRa, as evidenced by its better OP and BWT scores. We've also explored our method on another domain, law, with the free law subset of Pile dataset as our pre-trained corpus. We evaluate on unfair twos of the LexGlue benchmark. In our experiment, we assess the scalability of our block expansion method in terms of training loss and downstream task performance as we increase the number of added blocks. We also compare our method with the mixture of expert expansion method. We find that adding 8 blocks provides optimal performance with minimal cost compared to larger models, hence we adopt this as our default strategy. We've also analyzed the impact of the position where the identity blocks are added, either at the bottom or the top of the model, compared to adding them interleaved. We observe that adding blocks at the bottom results in poor evaluation performance, likely because it disrupts the model's foundation, causing errors to propagate throughout the model. Adding blocks at the top of the model preserves the initial model's performance, but its performance on domain-specific tasks is lower than when adding blocks interleaved. To investigate the extent of knowledge encoded during pre-training, we conducted a comparative analysis between LLAMA 2-7B and LLAMA Pro using the same instruction dataset. Our results showed that LLAMA Pro consistently outperforms LLAMA 2-7B across all tasks, indicating that our method effectively enables LLAMA Pro to encode more domain-specific knowledge during the pre-training phase.